Okay, so what I want to do is give you a little bit of additional information about Chapter 9 that we didn't necessarily get to um, on Wednesday. Obviously, this was not on the exam today, but you could see it on the final exam, so I thought I'd give you this stuff. Make sure you go watch the problems that we did on Thursday if you haven't done so yet, just so you know how to use enthalpies and things like that. So at the end of Wednesday's lecture, we talked about bond energies. And these are the energies that it would take to break 1 mole of a specific type of bond. So for example, if I've got a nitrogen-hydrogen bond, it takes 390 kilojoules per mole on average to break the nitrogen-hydrogen bond. So basically, if I've got a mole of these, it will take me 390 kilojoules of energy to break all of them. Now, the thing to know about bond energies is their averages. Not all nitrogen-hydrogen bonds, or maybe none of them, are exactly 390 kilojoules per mole. So, for example, I could have ammonia, which is NH3, like that, or I could have, what else could I have? I could have some other molecule with nitrogen and hydrogen in it. I'm trying to think of something off the top of my head. Maybe something like this. Just coming up with this dimethyl ammonium, whatever, where the nitrogen hydrogen bond here is the only one to that nitrogen. In this case, there were 3 of them. In this case, there's only 1. So this bond is going to be a little bit different strength than these. Or if I break 1 bond from the ammonia, the next 2 are a little bit easier to break. So not all of them are going to be exactly the same. So what all of these are kind of an average measurement of how much energy it would take to break those bonds, a mole of those bonds, right? So these bond energies aren't exact. So we can use bond energies to calculate heats of reaction or enthalpies of reaction, but it's just an estimate. So sometimes we want to know if it's exothermic or endothermic or close to 0. That's what we could use this for, so an approximation if we didn't have any other way to do our calculation to calculate delta H. Okay, so for an example, estimate the heats of combustion for ethane, C2H6 gas. So let's write the formula for this. So we have C2H6 gas plus combustion, remember that's with oxygen, produces CO2 and H2O. And those are the only 2 products if there's enough heat and enough. I'm going to do this as a liquid though. So we're going to do it 298, 25 degrees Celsius. So if we combust ethane with oxygen, well, the combustion is with oxygen. If we combust ethane and there's enough oxygen and enough heat, the only 2 products should be carbon dioxide and water. All right, so we got to balance this. I need 2 of those because I got 2. I got 6 hydrogen, so I need 3 waters. So I've got 4, 7 oxygens. So I need 3.5 or 7/2 oxygens. So right, 2. That's 4 oxygens. That's 3 oxygens. That's 7. So I need 7/2 oxygen. Okay. Now, normally, if I was just balancing reactions, I would double everything to make this a whole number, but I'm looking at what the energy is when I burn 1 mole of ethane. So I want to know delta H of combustion for ethane. So when I do that, I'm going to do 1 mole ethane, so I'm going to leave these all that way. Okay, so if I draw these structures, so we can see the bonds that are happening. And I got 7/2 O double bond O. I'm not drawing the full Lewis structure because I'm only worried about the bonds. I got 2 of these guys. We'll put these guys in parentheses so we know which are the molecules and it doesn't look like 20. And 3 waters. Okay. So when you're doing bond enthalpies, what we do is the energy of the bond's broken. So energy of bonds broken minus energy of bonds formed. And that will be an approximation for our delta H of the reaction. Okay, in this case, our reaction is a combustion. So let's look at this and figure out what we got. So I basically have 1, 2, 3, 4, 5, 6. So I've got 6 CH bonds that I got to break. And I've got 7/2, it's kind of a weird number, 7/2 O double bond O that I have to break. Over here, I'm going to form 2 C double bond O bonds. And here I'm going to form 3, actually I'm going to form 4 of these, right? Because I'd get 2 per molecule. So 2 times 2 is 4. Over here, I'm going to get 6 OH bonds. Oh, there's one more. I got to break the CC bond. So after I knock all the hydrogens off, I got to also break the CC bond. So it's going to be plus 1 CC bond. Okay, so let's make sure we got this. So I got the CC bond. I've got 1, 2, 3, 4, 5, 6 carbon hydrogen bonds. 7/2 times a double oxygen double bond. 4 COs because there's 2 C double bond O's per carbon dioxide, and there's 2 of them, so I got to do 4 of those. And then 6 OHs from the waters. Okay, so let's go to our table and figure out what our energies are. So a C single bond, C is 345. So I've got 1 times 345 kilojoules per mole. That 1 is a mole. So 6 moles times carbon hydrogen bond is, oh, good God, it's not on here. Carbon. Seriously? Carbon bromine. Ugh. I swear it was on here. Okay, so let me go find that real quick. So I just checked your book, and it's actually, still got a pen. The carbon hydrogen bond on average is 415 kilojoules per mole. So going back to here, so we got 6 times 415 kilojoules per mole. And then we got to add 7/2 times O double bond O. And that's right here, 498. Make sure you get the double bond one. So 498 kilojoules per mole. And then we're going to subtract off the products. Minus 4 times C double bond O. Right there, 741 kilojoules per mole. Minus, right, because we subtract off both products, 6 times OH. Oops. OH is not on here. Thankfully, I've got my book open still. And OH and OH, the heck? Oh, it's on top there. Sometimes I'm blind. Right there. 464. 6 times 464 kilojoules per mole. Okay, so I'm going to, this is approximately my delta H. So I'm going to do this. So this is 345 kilojoules plus 6 times 415, which is 224.90 kilojoules per mole, plus 7 halves times 498, which is 1743. Oop, there's no mole here anymore. 1743 kilojoules minus 4 times 741, 2964 kilojoules minus 6 times 464, 2784 kilojoules. And that's approximately our delta H of reaction. We'll see how approximate it is. So putting these all together, 345 plus 2490 plus 1743 minus 2964 minus 2784 screwed that up. 345, 2490, 1743, 2964, 2784. Negative, so I get delta H of this reaction, which is the combustion of ethane, is approximately negative 1170 kilojoules for that reaction we just did. If I go look that up, it's actually, so the actual value of delta H of combustion of ethane is negative 50, about 1560 kilojoules per mole. So we're off a little bit, but it does tell us that it's negative, which means it's an exothermic reaction. It just doesn't get it quite right because the bond energies aren't perfect; they're averages. Okay, so but that's how you can use bond energies, and that's how you use them. When you do it, you do energies of bond broken minus energies of bonds formed. So you break all the bonds in the reactants, and you reform them in the products. Okay, the last thing. So that's how we deal with covalently bonded systems. But what about ionics or ionic compounds? So when ions form, they're attracted to each other. So if we take a metal and a nonmetal and we ionize the metal, so we take an electron off of it, and we put that electron on the nonmetal, so that's electron affinity, we get a cation and an anion, and they're attracted to each other. And we measure that attraction for each other in a crystal by dealing with what's called lattice energy, or lattice enthalpy in this case. We call them lattice energies. The lattice energy is the amount of energy required to separate 1 mole of the compound into individual gaseous ions. So you can see we take our metal and our nonmetal, and the lattice energy is the energy it takes to separate these into their ions. Okay, so delta H, the lattice energy, is going to be greater than 0, significantly greater than 0. Because it's the energy I got to put in to cause the ions to come apart. And they're pretty well attracted to each other. Okay, so lattice energy is going to be greater than 0. Again, it's the energy required to separate 1 mole of solid into individual gaseous ions. All right, so lattice energies we can't measure. Right, that's not something we can go into a lab and measure. So we have to find an alternate way to calculate these. And conveniently, there's this thing called the Born-Haber cycle. And the Born-Haber cycle is the process by which an ionic compound is formed. And part of that is this attractive force between these ions that produces the lattice energy. So this is the full cycle. So let's take a look at this and see what it means. Okay, right here is where we would be if we were combining our metal and our nonmetal. The metals in this case is a solid. This is cesium, so it's an alkali metal. and fluorine, which is a halogen. So cesium is going to form +1 ions, and fluorine is going to form a -1 ions. So the formula we're going to get is cesium fluoride, CSF, solid in the end. Okay, so this bottom spot where energy is lowest or enthalpy is lowest is where we have our cesium fluoride. Okay, so from the elements, which is cesium and fluorine, in their elemental states at 25 degrees Celsius, this direction would be the heat of formation, because that's going from our elements in their forms at 25 degrees Celsius and 1 atmosphere pressure to our product, cesium fluoride solid. Okay, that's our heat of formation. What we're looking for is this lattice energy. So to calculate that, we're going to do, so this is the direct way to get to heat of formation. What we're going to do is this second route. We're going to make our cesium fluoride how we would normally have to do it. Okay, so we're going to start with our cesium metal, solid, and our fluorine gas. Okay, and fluorine's F2, so we only need half of it. So the first thing that we do, because we need to get into the gaseous state, is convert the cesium solid to cesium gas. Remember, ionization energy and electron affinity deal with elements in their gaseous state. So ionization energy is the amount of energy required to remove an electron from an element, from an atom or ion, in its gaseous state. Okay, so what we're going to do is put enough energy in to create this, or to convert the cesium to cesium gas. And that process is called sublimation, so it's delta H sub S, and that's the energy we have to put in as heat for that to happen. Okay, once we get that as a gas, we need to ionize it. We need to make the cesium +1 and the fluorine minus, right? So the cesium, we pull an electron off, and that's called ionization energy. So that's the ionization energy that's required to remove an electron from cesium, a mole of cesium. All right, so then we're here. We have the cesium in the state it needs to be. It's the ion in the gaseous state. Now we have to deal with fluorine. Okay, remember, fluorine's F2, so it's got a single bond between it. So what we need to do is break that bond. Remember, D is the bond energy for fluorine. So what we're going to do is take the energy required to break a mole of those and take half of it, right? Because we only need half. So because when we break half of it, we get 2 of them, and that's enough to react with all the cesium. So I'm going to take half of the bond energy, which is 79.4. Okay, so now I've got cesium plus and fluorine F. I need to ionize the fluorine by adding an electron to it. That's called electron affinity. Remember, electron affinity is the energy that's either required or released when an atom or ion gains an electron. And again, this is in the gaseous state. So we take fluorine and we add an electron to it, and the electron affinity for fluorine is -328.2, which means it gives us energy back. Okay, so putting an electron on fluorine, so now we have our cesium ion, cation, and our fluorine anion. They're attracted to each other once they're formed, and the attraction is the lattice energy. And in this case, it's negative. We're doing the negative lattice energy, because remember, lattice energy is the energy to pull them apart. We're actually putting them together right now. So we're going to do the negative lattice energy, which would be the opposite of lattice energy, where lattice energy is putting them together or pulling them apart. We're putting them together, so we're putting a negative in front of it. And when we put them together, it releases quite a bit of energy, you can see, because they're attracted to one another. Okay, so that's our full cycle. So we went from heats of formation, which basically just, the enthalpy of formation, which basically takes our elements and makes what we want. And the other route is actually creating each individual piece and getting back to cesium fluoride just like this does. This route, the straight to HF from cesium metal and fluorine gas straight down to cesium fluoride, isn't what really happens. It actually got to go all the way up and around. Okay? We know this because it's measurable. We know all the other ones because they're measurable. The lattice energy is not measurable. But because this is a full cycle, we can use all of these to calculate this. Okay? So if we start at 8, the heat of formation, this guy, is equal to this whole process. Okay, so I'm going to write the heat of formation is equal to the heat of sublimation, that one, plus the ionization energy, that one, plus 1/2 the dissociation energy, that one, plus the electron affinity, that one, and then plus the negative lattice energy because we want them attracted to each other, which is why that is. So instead of doing plus minus, I just did the negative lattice energy. Okay, so now we can actually do this calculation. But to do this calculation, I'm looking for the lattice energy because I've got all the other ones. This one shows us what the lattice energy is, but that's what we'd be looking for in normal situation. So I'm going to rearrange this equation to put the lattice energy on one side and everything else on the other side. So when I do that, I get the lattice energy is equal to the heat of sublimation plus the ionization energy plus 1/2 the dissociation energy plus the electron affinity minus the heat of formation. Putting the numbers in, I get 76.5 plus 375.7 plus 79.4 plus minus, so that's just going to be minus 382.2. Minus minus is going to be plus 355 or 553.5. When I do the math, I get the last energy of 756.9. Remember, it's positive. If I want to take the negative, like I could do here, I got to do negative both sides. So that's how we figure out lattice energy. It's not measurable. We have to find another route. So we know the heat of formation of our compound, and we just follow this all the way around. And we equate the two. We equate this with this, and we just put the numbers in and do the math. Okay, that's the Born-Haber cycle. It's the cycle showing each of the steps by which an ionic compound is formed. All right, we'll stop there. I just wanted to give you those so that you have that information because you might see that on the final.